G'day grade 12s, I'm Taryn Roberts, and in our BOO series of STEM in Action today we'll be looking at part 3 of electrodynamics. So the topic of electrodynamics covers electrical machines as well as alternating current. In part 1 we looked at AC and DC generators. In part 2 we looked at AC and DC motors. And therefore, to complete our entire topic of electrodynamics for grade 12, we need to now consider the section called alternating current. In this section, we'll be looking at AC and DC current, or alternating current compared to direct current. And we'll also be considering the voltage versus time and current versus time graphs for AC, or alternating current. And then we'll be doing some calculations involving AC, alternating current. So let's get started. What is alternating current? It is the electricity generated or produced from AC generators. Remember these AC generators we discussed in part 1 of electrodynamics. The symbol is AC, or the abbreviation is AC, and the symbol is shown in the electric circuit diagram on our right over here. Very different from a direct current symbol. This symbol also indicates the sine graph, and that reminds us that the direction of the current changes periodically. In fact, every 180 degrees. That's why we are calling it alternating current and not direct current. AC, or alternating current, is used in households and industry. And so let's go find out a little bit more about AC. What are the advantages? It's much easier to generate alternating current than direct current. This is quite interesting because for most of your high school physical science, you've always been learning about DC, or direct current, your positive terminal and your negative terminal. And now in grade 12, you actually finally learning about the most commonly used type of current, which is your alternating current. And we found that it's much easier to generate AC versus DC. It's also easier to convert alternating current to direct current than converting direct current to AC. For AC, the voltage can be stepped down or stepped up using transformers. High frequency in alternating current allows them to be used or to be suitable for motors. Now let's consider our power stations. There we have a little schematic of a typical power station. Obviously this covers vast area, and we've just now brought this in so that you can see how the current that gets to our household, where it actually starts. So our power stations over there, they generate alternating current. And this alternating current is stepped up using step-up transformers. This takes high voltage to low current. This allows energy loss to be less, and that energy loss, we're talking about heat lost. Okay? And so as this current is traveling through the cables, there's less energy lost because it's traveling at high voltage, therefore low current, and less heat is given off as it travels from the power station through and before it gets to our home. As this current travels, it gets to a substation, which we often hear about during load shedding. And now as it steps down, it is now at a low voltage, generally 240 volts, and this gives us a high current which we are able to utilize in our households, where we can use it for our heaters, for our fans, and even in industry and business, etc. So let's consider some definitions, namely the root mean square. Grade 12s, when we hear alternating current, we need to think RMS, root mean square. The root mean square value of AC is the direct current or voltage, which dissipates the same amount of energy as AC. Now, if that is a bit confusing, let's go and explore this using graphs. But before that, we have a IRMS, current root mean square and a VRMS voltage root mean square. Don't panic, these equations are on your data sheet. So our IRMS, current root mean square, is equal to I max divided by square root 2. And our VRMS is equal to V max, the voltage maximum, divided by square root 2. So let's look at the graphs for AC circuits. You must be able to know or reproduce these graphs for either voltage or current in an AC circuit. What's really nice is the graphs are the same shape. It's your sine graph. So here we've got a sine graph, and that shows one cycle. We've got a maximum voltage there and a maximum voltage there. So in one cycle we have two maximum peaks in the positive direction and the negative direction. And an average across there is what we call the VRMS, which would be corresponding to the maximum in a DC circuit. If we look at this in terms of current, we get the same shape for one cycle. We get a maximum current in the positive direction, a maximum current in the negative direction, and an average IRMS, as you can see over there. So let's have a look at these in terms of circuits. If we take an example where we've got a DC circuit, how do we know that it's a DC circuit? Well, the symbol used for our power source is our positive terminal and our negative terminal over there. Its maximum voltage which it can provide, or maximum energy that it can provide to the circuit, is 100 volts, the EMF. Similarly, if we compare this to an AC circuit, we know that because that's the symbol for an AC power source. Its VRMS, not its Vmax, its VRMS is that same voltage, which would be its corresponding maximum voltage in a DC circuit. Do you see how those equations now make sense when we look at it practically in a circuit? So let's continue. If we had to draw the graph for potential difference, or EMF versus time, it's constant. That maximum voltage remains constant, so that's why we've got a horizontal line at 100 volts. Let's go look at this graph for an AC circuit. There's our sine graph, which we saw earlier. So for EMF, voltage over time, we have a sine graph or sinusoidal graph, and we can see that Vmax is not 100. Okay, Vmax is that peak. So we've got a peak of positive 142 volts and a peak here of negative 142 volts. But the VRMS for this AC circuit is 100. Can you see how these values correspond? So the maximum potential that can be supplied in a DC circuit is equal to the VRMS in an AC circuit. I really hope this is starting to make more sense, grade 12s. So we need to go and find out what is the power that is generated in an AC circuit. So let's go look at some derivations using the same example. So there are our graphs for a DC circuit showing the maximum voltage, and for an AC circuit showing VRMS. We know, and we've been told earlier, that VRMS equals Vmax divided by square root 2. In this case, we know that VRMS is equal to 100 volts. There we go. VRMS is equal to 100 volts. We can read it off the graph. And we also know in this section here, in our DC circuit, our Vmax, or our V or EMF, is equal to 100 volts. All good. According to Ohm's law, resistance equals V over I, and so in terms of RMS, we've got VRMS divided by IRMS. And so we can solve for VRMS, and that gives us IRMS times the resistance. For our DC circuit, Ohm's law states that the resistance is equal to the voltage divided by the current. And so V equals I times R. Do you see how similar they look? V equals I times R, and for an AC circuit, VRMS equals IRMS times R. If we consider power, our power formulae are P equals VI, which equals I squared R, which equals V squared over R. So those are our power formulae, and we can now give this corresponding power formula in terms of VRMS and IRMS. There they are, right there. So for alternating current or AC circuits, we should be able to calculate the power generated by that circuit. Again, do not panic because all these formulae are on your data sheet. So we've got IRMS, which is I max over square root 2, VRMS, which equals V max divided by square root 2. The following two formulae for current and voltage are not on your data sheet, but here they are. They are basically just the formulae for those sine graphs. So it's an expression for current, an expression for voltage. They are not on your data sheet, but what is on your data sheet are all the formulae for power, calculating average power in terms of IRMS and VRMS. So all these equations over here can be found on your data sheet. So let's go and see how all these terms, concepts, graphs, and equations can be asked in a typical exam question. So for this application section, we will consider paper 1, November 2019, question 9.2. So in question 9.2, it reads, a 200 ohm resistor is connected to a DC voltage supply. Let's underline that because now we know we're working with DC voltage, as shown in diagram A. So there's our DC source in diagram A. The energy dissipated in the resistor is 500 joules in 10 seconds. The same resistor is now connected but in a AC circuit, as shown in diagram B, and 500 joules of energy is also dissipated in 10 seconds. 9.2.1, determine the term RMS voltage of an AC source. All right, so I've prepared the answer, and this we covered in the series or in the segment. We covered this when we discussed RMS, root mean square. Remember, it can be root mean RMS current or RMS voltage. For question 9.2, we're looking at RMS voltage potential difference. So the AC potential difference, which dissipates the same amount of energy as DC potential difference. This is called the RMS voltage of an AC circuit. So I'll read that again. The AC potential difference, which dissipates or gives off the same amount of energy as DC potential difference, is the RMS voltage for that AC circuit. That's all theory, and that's worth 2 marks. 9.2.2. So calculate the maximum voltage of the AC circuit. So we're looking for V max, not directly VRMS. But possibly we'll have to go via VRMS to determine V max of the AC circuit. So we're looking at the AC circuit. So we can go about it as follows. If we look at all the information that they've given us, nowhere have they spoken about V max. But alarm bells, we've got joules, we've got time, and we know that power is equal to the rate at which work is being done. And so that equals 500 joules divided by 10 seconds, which equals 50 watt. We can write it 50 W, okay? That's a start. And we know, if we come to our data sheet, we're wanting V max. So if we've got power, and now we need to look for a formula that has power and VRMS in it. Because the minute we have VRMS, we know that VRMS equals V max divided by square root 2. So we're looking for a power formula with VRMS in it, and we were given the resistance of the resistor. So we're looking for VRMS and a resistor in the power formula. So let's go have a look at them. There's a VRMS, but no resistance. Ah, there we have it. We've got VRMS squared divided by R. So let's go and use that. So we can say, let's say power average. So P average from our data sheet equals VRMS squared over R. And we know that this equals to 50 watt because we just calculated it over there. And let's substitute, or let's rearrange the formula. So VRMS squared equals P average times R, which equals 50 times 200 ohms. That gives us an answer of 10,000 volts. And well, let's leave the units out for now, 10,000. And so therefore, if we square root it, VRMS equals 100 volts. I know this sounds all like we're done now, but honestly, let's go check if we've answered the question. It says calculate the maximum voltage. I do not see Vmax over there, which means I'm still busy with this question. Grade 12s, please always check. Have I answered the question? And so we know that Vmax and VRMS are linked via VRMS equals Vmax over square root 2. And we know that this answer equals 100 volts because we got it from here. And so Vmax would equal square root 2 times 100. Let's go and pop that into our calculator. So we go square root 2 times 100. And our answer is 141,42 volts. That's question 9.2 answered from question paper November 2019. Not so bad. And this is all in the section of alternating current. All right, grade 12s. Let's try another application question. This time it's coming from paper 1, November 2018, and we will be considering question 10.2. So let's go and have a read. The voltage output of an AC generator is shown below. Write down the maximum output voltage, or in other words, Vmax, for this generator. So 10.2.1. Now, grade 12s, a hint. If they give you a graph in a question paper, the majority of the time, your answers would just have to be read off the graph. So don't just delve straight into equations. Use what they give you. So let's go have a look. If we look at the shape of the graph, we've got our perfect sine shape over there. And we know there's Vmax and Vmax in the opposite direction. And so clearly, from the graph, Vmax equals positive 340 volts in this case. If you said Vmax equals negative 340 volts, it would also be right because there are two maximums in one cycle. Now let's move on to 10.2.2. A stove is connected to the generator above and delivers an average power of 1,600 watt. 10.2.2, calculate the RMS voltage, or VRMS, delivered to the stove. First things first, the minute I see average power, I'm going to go and say P average equals. And I'm going to go to my data sheet and go and find an equation. Now, which equation would I like to get? They asked me for VRMS. So I need an equation that contains VRMS. All right? So I've got, from my previous question, I've got P average equals VRMS squared over R. And I've also got another equation here, VRMS IRMS. Now, I need the RMS voltage. What have they given me? I've got power. And I know from here, I'll be able to pop that into the Vmax over square root 2 formula. But now, do I have R? They're asking us to calculate the RMS voltage delivered to the stove. Now you see, grade 12s, I told you straight away that you mustn't delve into questions. So if I look at 10.2.2, I need VRMS. I don't need the average because VRMS is equal to Vmax over square root 2. Do I have Vmax? Absolutely, they asked me that initially. So Vmax equals 340 divided by square root 2. Pop that onto my calculator, 340 divided by square root 2. And that gives me 240,42. It's voltage. There we go. We can now move to 10.2.3. Now they're talking about resistance. So if I've got VRMS and I'm looking for resistance, on our data sheet there's an equation that links the two. VRMS squared and divided by resistance equals the power. So let's use that formula. Average power equals V squared RMS over resistance. We know that this average power equals 1,600 watt. We've got VRMS, so we can invert. Remember, this is over 1. We can invert this, and we can say 1 over average equals R over V RMS squared. And so R would equal V squared RMS over the power, which equals 240,42 squared over the power 1,600. And let's go work out that resistance. 240,42 all squared divided by 1,600. Oopsie. Let's go do it again. 240,42 squared divided by 1,600. My final answer for the resistance of the stove is 36,13, and resistance is measured in ohm. So they asked you to calculate the resistance of the stove, and if all our maths is correct, we worked it out, and it's actually equal to 36,13 ohms. So in part 1, we looked at generators, both AC and DC. In part 2 of electrodynamics, we considered AC and DC motors. In this part of electrodynamics, we considered alternating current. That covers all 3 sections that make up your entire electrodynamics syllabus for grade 12. Now we're going to, in our application section, we're going to cover a question that hopefully deals with all 3 sections as they would cover it in an exam question. So our application section would cover paper 1, September 2018, question 9. Let's have a read. The simplified diagram below represents a generator rotated in the direction on the diagram. So we've got the rotation there. 9.1.1, state the energy conversions that take place in the generator. Now, if you can remember in part 1, we can answer 9.1.1. A generator, we have mechanical energy is being converted into electrical energy. And if you're doubting yourself, let's have a look at the diagram. In the diagram, nowhere does it show us a power source, so we're definitely not starting with electrical energy. But they also tell us that the generator or the coil is rotated, which means that the rotation is a precursor. So there is mechanical energy, and we know it is converted to electrical energy, so we are inducing an EMF. 9.1.2. The generator is rotated clockwise, as indicated in the diagram. What is the direction of the current in section PQ? Just going to highlight that there in my diagram of this device. Write down only P to Q or Q to P. So again, grade 12s, you cannot go and say upwards or into the page or from left to right. You need to use the notation indicated in the question. So let's go and see. We're talking about direction. For generators and motors, we have two rules. For generators, we generate the right answer. So we have the Fleming's right-hand rule. And for motors, we remember he motored off and left. For motors, we have the left-hand or Fleming's left-hand motor rule. So what are we dealing with here? We are dealing with generators, so we generate the right answer. Remember our recall technique. So we're going to use Fleming's right-hand rule to determine the direction of the induced EMF or current in this case. So what do they tell us? Fleming's right-hand rule for generators: father, mother, child. Father gives us the direction of force. Mother, this first finger, gives the direction of the magnetic field, and then we've got the direction of the current. Out of the three, what do we have? We've got the direction of magnetic field. That's going from north to south. Over here, if we look at PQ, if we look at that coil as it is, it's in the horizontal position. For it to rotate clockwise, PQ is going to go up. If I only look at one aspect of the coil, PQ, which I'm going to signify as my left hand, it's going to go upward, okay? Because they told us the rotation is upward, so we know the rotational force. So if we use our right hand, we've got north to south, our first finger indicating the direction of the magnetic field. My thumb is the direction of the mechanical force or the force of rotation. PQ is rotating, or the coil is rotating clockwise, so PQ is going to go up, and so my middle finger gives me the direction of the induced current, and in this case it's going to go from P to Q. I really hope this gives you a bit more practice in how to apply Fleming's right-hand rule. So from our rule, we know that the current, induced current, will be from P to Q. Now we can move on to question 9.2. Generally, in a question for electrodynamics, the first section covers generators or motors or even both, and the second section of the question will deal with alternating current. So let's look at question 9.2.1. The diagram below shows a simplified version for part of a household wiring circuit. The voltage supply in a certain house is 200 volts, and a light bulb has a resistance of 12 volts, and a kettle has a resistance of 24 volts. And these are used at a certain time as shown in the diagram. So now before we even look at question 9.2.1 or 9.2.2, let's go and unpack that circuit diagram over there. Number one, the symbol. I know I have an AC circuit. Check. Second of all, I've got 230 volts. I know that that is my VRMS. Then I've got two resistors. And how are those resistors connected? They are connected in parallel. So I could possibly have to go and find out the total resistance, but remember, just if we do, we need to know how these resistors are connected. And there's a branch here, and so we know that these resistors are connected in parallel. So let's go and see. We need to calculate the Vmax, or the peak voltage, or the maximum voltage for the domestic supply. And we know that Vmax and VRMS are related in the equation. VRMS equals Vmax divided by square root 2. We have VRMS, and so we can use the formula VRMS equals Vmax divided by square root 2. We need to calculate Vmax, so therefore Vmax becomes the subject of the formula. And I've got square root 2 times VRMS. From my diagram, I know that VRMS is equal to 230 volts. So when I pop that onto my calculator, times 230, equals 325,27, it's voltage, There we go. I've got Vmax sorted. Let's move on to 9.2.2. They say the average power dissipated if the two light bulbs and the kettles are used at the same time. We need to calculate that average. We know we've got VRMS. We also need to calculate the average power. If we look at our data sheet, again, just by coincidence that we happen to use the same formula, we need to find average power. We've got VRMS. So the obvious thing to find out now would be the resistance total for the circuit. This is going to take us back to grade 10 electric circuits. So we know it's a parallel connection. So 1 over R total equals 1 over R1 plus 1 over R2. Please, if you've forgotten this, we definitely would be recapping it in our electric circuit section of the series, but if not, go and have a look at your grade 10 textbook. This is the formula for calculating a range of resistors in parallel. And so this would equal 1 over 24 plus 1 over 12. Our lowest common denominator, this gives us 1 plus 2, 3 over 24. And remember, this is 1 over R total. That's not the answer. My answer is not 3 over 24 because I want R total. So I invert my left-hand side. And what I do to the left, I do to the right. And I invert my formula there, my fraction there. So I get 24 over 3. And that equals a lovely number, 8 ohms. Are we done? Absolutely no, because the question says calculate the average power. And we've got R and we've got VRMS from our graph. And there's a power formula on our data sheet that relates these two as average power equals V squared RMS over R. My V squared or my VRMS equals 230 volts. Where did we get that from? Well, from our circuit diagram. Our VRMS equals 230 volts. And that's divided by our total resistance of 8. And if we pop that into our calculator, we get an answer of 6,612,5. We're looking for power. And the formula for power, or the units for power, is the watt. So grade 12s, we have completed 11 marks in our question paper. We've looked at the entire question 9, which covers the electrodynamics section. And as I said, 9.1 dealt with generators or motors and could possibly even have both sections in there. And the second part of the question always looks at alternating current. So in this segment, we have completed the entire topic of electrodynamics. I remind you again, part 1 we looked at AC and DC generators, part 2 we looked at AC and DC motors. In this segment, part 3, we considered alternating current, and we just looked at question 9, which covered an entire electrodynamics question. Grade 12, I really hope that this builds your confidence and you feel way more confident to tackle electrodynamics questions. I encourage you to practice by going through more questions in your Boost Prep Pack. That's all from me.